So we're going to carry on from where we left off. So here is my structure of array simulation. I'm running 100,000 particles here. You can see that the drawing's taking about 500, 600 microseconds, and the update's taking about 21,000 here. So, you know, reasonably good. We've got nice interactive frame rates. We can zoom in fairly well. What we sort of discussed the bottleneck was at the moment is this drawing is taking a fair amount of time. So what we're going to look at is how we can mitigate that and make the drawing a lot quicker. So here's the version that we're going to look at, and you can see here our drawing is only taking about 20 microseconds. However, if we add in this texture buffer update as well, you can see now that my simulation is split into two parts. So I've got a buffer update which is taking about 300 microseconds plus this draw which is 20 microseconds, which is still much faster than this combined total of the data. So this is doing a lot more work now. You can also see that my update is slightly less, and again we'll talk about that because I've slightly restructured the code as well. So this version is the Textual Fetch version, and what we can see here, so again the data is more or less the same as before. However, what we do now have is a few extra components. So we have our data in structure of our array format as we had before. So we've got our positions and our directions, acceleration and speed. We've got our VAO that we had previously. We've got a few other parameters here. We've got a texture buffer and two buffer IDs. These are going to be used to allow us to copy data to the GPU per frame. Now, the concept behind texture buffers is OpenGL allows us to create textures. It also allows us to create arbitrary buffer objects that can just contain floating point information, or various other formats as well, but in this case floating point information, and we can sample into that as though it were, in this case, an array of vec3s, and depending upon the vertex index that we're sampling, we can sample into that data and get the correct floating point value. So this is a really efficient way of passing large amounts of data into the GPU for reading, and it's a very easy read-only sort of process. To start with, what we need to do is to create some texture buffers. So there's a function in here which is going to initialize our texture buffer object. So I'm going to generate two texture buffers. This will then populate the ID for these texture buffers into this array here. And this is what OpenGL uses for its object identifiers. We are then going to bind that first texture buffer object, and we're going to allocate some space for it. So what we're doing here is we're saying our buffer data is the size of our position array times the size of a vec3. So in bytes, that's how big that buffer is going to be. We then need to associate this buffer with an OpenGL texture, because the OpenGL texture gets activated to be read by the Textual Fetch function within the shader, which we'll look at in a little while. So while this buffer is there, what I'm going to do is generate an OpenGL texture ID, and this is what we use to activate when we're enabling the shader to do the drawing, to say this is where I want you to read the data from. So we generate the texture. I'm setting that to be texture unit 0, so we need to read from that texture unit and set up that texture unit when we do it. When we look at the drawing routines, we'll see that in action. We're binding that texture as a buffer texture based on this ID here, and then we're just associating the texture buffer that we generated with this texture. And you'll notice here it's in the format of GL RGB 32F, so that's a vec3 32-bit floating point value. So that will be my X, Y, Z components that I'm going to read in. I'm doing exactly the same, creating another buffer here, which is being used for my next component, which is the directions. Binding all those buffers through, all ready to be used later. Now, I've also got this method called update texture buffer. This is going to get called each frame, and in fact, as you can see now, I've split this out. I only call this when we do a draw. So we will have a slightly bigger bottleneck now in our draw component, but when we call paint GL, what happens is we first make a call to update the texture buffer, then we make a call to do our draw. So we could call this every frame when we do the update, but that's wasteful because we only need it when we draw, and OpenGL will do the, while those calls are being called, OpenGL will obviously make sure that only one thing can happen at once, because OpenGL is inherently not particularly multi-threaded. If we were using a more modern graphics API like Vulkan or perhaps Metal, then we could be doing some other sort of more complex multi-threaded streaming in the background. That's for a different lecture as well. So update the texture buffer, then do the draw. And when we do the draw, we've just got to make sure that the textures that we're using are activated in the correct texture units so that OpenGL knows which ones are which. Just to go back to the shader, when we set up our shaders, we need to set the uniforms for the samplers to correspond to the texture units that are there. So I'm saying sampler for position is at texture unit 0, and the sampler for the direction is at texture unit 1. That then corresponds to me activating texture unit 0 and binding the position buffer, activating texture unit 1 and binding the direction buffer. Then I'm binding my vertex array and drawing my number of points there. So now one thing you'll notice is, in this case, I've not actually created any other buffers. So whilst I've made a call to gen vertex arrays, which we must have a vertex array generated and bound, there are no other buffers associated with this. So I haven't created any vertex buffers that have any vertex data. So if we look at our vertex shader now, you'll notice there's no input to this vertex shader. And in fact, all I'm doing in the vertex shader is having these two samplers. So this is at location 0, this is at location 1. Now, we could bind these with layout prefixes, but that doesn't work on the Mac, and I'm trying to make this code to work on the Mac and everything else. So that we could actually make this slightly more efficient with modern OpenGL, but I'm targeting 4.1, so it's not there. So every time the draw arrays gets called, this is invoking the vertex shader, but obviously the vertex shader at the moment has got no inputs, so it gets called, but it hasn't got any data being passed each time. So instead, the Textual Fetch is being called, and what we do is we pass in the vertex ID, and the vertex ID of this shader is basically every time we make a call to GL draw arrays, we pass in where to begin and the amount. Vertex ID gets incremented each time, and we're using that to then sample into that buffer to get a vec3, which is our position, our direction. That then gets passed on to the GeoShader for the drawing, and so on. So it's very much the same as before. You'll also notice now that update is exactly the same as we had previously, reset particles, everything else is the same. All we've done is got rid of the copying the data, and we're just now copying the buffer data instead. If we have a quick look, let's see whether we can see whether our hotspots in profiling have changed much. So I'm going to just run this up again. There goes our debug there. Let's grab some runs of this code and see what's happened there. It appears to not really have done much. What's going on there? Let's just stop that and start again. So show That's because I put, there we go, I put it in the wrong place. Let's start and run this again. So the debugs were in the breakpoint was in the wrong end, the process never got to run. So here's our program running again. It's trying to run. I'm not sure what's happening there. Let's stop again and start run. Hit the breakpoint and give me my continue point. So it does look like it's doing some recording. Unsure. What's happening there? That's very odd. Let's just get rid of these breakpoints and try and run it. Seem to be having a little bit of an issue. So it's running there. Always the way when you're generating a video, isn't it? Let's try again. So let's set a breakpoint there and a breakpoint at the end of our program. Let's run our program, hit our breakpoint, there we go, hit continue. Now it's doing the recording. Should have now hopefully recorded enough samples to get an idea. Generating our profiling data, and we can look through and start to look. So now you can see our graphics is sort of increased slightly more. The hot paths are still more or less the same as previously. Let's have a look through our sort of summary of events. Events, breakpoint 1, CPU usage. Still one of the biggest things we've got is the accessing of the VEC3 in our code there, which is, you know, generally quite fast. And again, if we go up and see where our hot points are now, we can see that the elements in our code are paint is taking 27. The render text is expensive, as we already knew there. But if we start just looking at the grid components, let's see what comes up. So grid constructor, init grid, reset particle is causing a lot. So yeah, I mean, it's hard to really see without digging in and getting some more profile time there, but we're definitely a lot more efficient here now. And again, if we just jump back into this and have a look at one of the demos running now. So this is with, let's do 1, 2, 3, 4, 5, 6. So big amount of particles now. So that's 1 million particles running, and you can see now that drawing is no longer a bottleneck. Buffer update, slight bottleneck, but our update of all the particles is definitely the bottleneck that we're facing now. And our slow path of our code is definitely this element here. And actually, one of the things that we can begin to look at on doing this is if we were to fire up the task manager and have a look at what it's doing, we should, it says, be able to start looking at what's going on. So the one thing that's really sort of doing stuff at the moment is we've got our CPU there. If we open up our resource monitor and have a look and start filtering, what we'll see is that we're not really utilizing our CPU in any sort of real meaningful way. So you can see that I've got, you know, my CPUs are doing something, but most of these CPUs aren't particularly being tasked with doing too much. I mean, it's hard to tell because I'm recording a video as well, so other apps that I'm using at the moment are going to be using cores. But running this process, I would like to be able to see that my one app that is running here should be, you know, using all the cores and being a lot more efficient. And I know for a fact at the moment that this application is only using a single core because I haven't written any multi-threaded code. There'll be a little bit that Qt is using, but there isn't much else that's actually doing much. So you can see here it's got 10 threads. It's only using about 8% of the CPU, and the average CPU usage is very, very low. So our next way of making this better is going to be to try and increase how that works.